let's start with the next chapter. Try and see if I can zoom in. So this is chapter 5, resampling methods. Let's start with this wall of text. Resampling methods are an indispensable tool in modern statistics. They involve repeatedly drawing samples from a training set and refitting a model of interest on each sample in order to obtain additional information about the fitted model. So reading this first sentence, this reminds me, for example, of confidence intervals. It's quite similar to what we were doing at one point, where we were creating linear models on a single predictor variable. So we were fitting a line, but that line was the data that we were using. We had taken, like, I think it was 5,000 data points, but instead of looking at the 5,000 data points at one go, we had partitioned the data into 50 sets of 100 data values. And for each 100 values, we were getting a slightly different beta naught and beta 1. And in many ways, that was giving us an idea of the confidence interval on the parameters that we were fitting. Let's continue reading. For example, in order to estimate, this is exactly it. In order to estimate the variability of a linear regression fit, we can repeatedly draw different samples from the training data, fit a linear regression to each new sample, and then examine the extent to which the resulting fits differ. And I'm going to open RStudio. I may have the script for what we had done during chapter 3, which is quite similar to what we've just read over here. And it was this one, right? Let's see. At least I think it was this one, yeah. So playing God, as always, you know your beta naught and you know your beta 1. These define the true line, the true model. Playing God again, you know the parameters of the epsilon error term, those parameters being the mean and the standard deviation. We define the endpoints of the input data. So our input data is greater than or less than 5. We decide that we're going to generate 5,000 observations using the uniform distribution, and then using the parameters that we've decided at the outset, create the y as a function of the x. And in fact, if we run this first block of code, this is all the data. And it looks like that because I've assumed the slope parameter of 0, which isn't too interesting. Let's change it to 2. This is chapter 3 territory, isn't it? Where the response variable, the output variable y, takes on numerical quantities. And then we said, let's just look at the first data set. Now this isn't resampling. And when we go back to the book, we'll see exactly what we mean by the RE in resampling. But we had said, for example, the first data set will actually only consist of the first 100 observations. And then we use the LM, the linear model function, to fit a line to the first data set, the second data set, the third data set, the fourth data set. So there's a lot going on, but if I run this and oh, so this is each data set, by the way. I think this is the last one. There's the one before it, the one before that, the one before that. So there's a total of 50 of them. You can see all of them like this by scrolling through the different charts. And if you ask are for beta 1 estimates, unfortunately, they have this header, which clutters things up slightly. But the idea is that you get a different, each 100 data points give you I'm referring to it as a slightly different. The variability would depend on the error term, for instance, and the number of data points that you're using. And in fact, oh, you can remove the header by using unname. So I actually placed them all in Z. These are the different beta 1 hats. There are 50 of them. R is telling you this is the 46th one, 47, 48, 49, 50. And they're all relatively close. Again, you can't see me, but I instinctively mimic air quotes with my hands. They are relatively close to what as the role that we're playing of an omnipotent being, that value that we set at the very beginning of this code. So they're all very close to the, whatever we mean by very close, yes. They're all very close to the true. And in fact, some of them, and coincidentally, we have 3 consecutive ones over here. They are at least the 2 decimal places. Those 3 data sets, their estimate for beta 1 happens to coincide perfectly with the true beta 1. Can do a summary. So think of the minimum and the maximum as your worst estimates, under and overestimating as always. And you even get a histogram. And then you can manually look at the standard error, etc., etc. So I chose to go back to that code that we had used way back when we were going through chapter 3, because it's probably going to help us, or it hopefully helps us over here. As always, exercising as much discipline as I can between these sessions to not look at the material until we're doing it together. This way, to a certain extent, we're all viewing it for the first time. And we've just read, for example, in order to estimate the variability of a linear regression fit, beta 0 hat, beta 1 hat, etc., depends on the number of predictor variables, we can repeatedly draw different samples from the training data, fit a linear regression to each new sample, and then examine the extent to which the resulting fits differ. Such an approach may allow us to obtain information that would not be available from fitting the model only once using the original training sample. Resampling approaches can be computationally expensive because they involve fitting the same statistical method multiple times using different subsets of the training data. However, due to recent advances in computing power, the computational requirements of resampling methods generally are not prohibitive. In this chapter, we discussed 2 of the most commonly used resampling methods, and these are cross-validation and bootstrap. Bootstrap's the one I'm often using in my own professional employment. Both methods are important tools in the practical application of many statistical learning procedures. For example, cross-validation can be used to estimate the test error. And remember what test error is. We had the opportunity to discuss this yesterday in the context of the S-market data, where we ignored the last year of data, was that 2005? And we treated it as our test data. So we fit the model, or we fitted the model. Were we using, I think it was logistic regression, correct? We fitted the logistic parameters based on the data till end of 2004. And then we used the preceding year's info to actually create the test error rate. For example, cross-validation can be used to estimate the test error associated with a given statistical learning method in order to evaluate its performance or to select the appropriate level of flexibility. This process of evaluating a model's performance is known as model assessment, whereas the process of selecting the proper level of flexibility for a model is known as model selection. And what is flexibility? What's flexibility? That trade-off between bias and variance. We could go back to chapter 2, but let's continue reading on for the time being. The bootstrap, so now this is not cross-validation, this is bootstrap, is used in several contexts, most commonly to provide a measure of accuracy of a parameter estimate or of a given statistical learning method. Starting with cross-validation. In chapter 2, we discussed the distinction between the test error rate and the training error rate. The test error is the average error that results from using a statistical learning method to predict the response on a new observation. What is a new observation? The book goes on to say a measurement that was not used in training the method. And remember, training the method is simply selecting the model and fitting the parameters. Given a data set, the use of a particular statistical learning method is warranted, so it's kind of like you would approve it, if it results in a low test error. The test error can easily be calculated if a designated test set is available. Unfortunately, this is not usually the case. In contrast, the training error can be easily calculated, and in fact, a lot of the different model types that we've seen, the way they're set up, they select the parameters that minimize the training error rate. In contrast, the training error can be easily calculated by applying the statistical learning method to the observations used in its training. But as we saw in chapter 2, the training error rate often is quite different from the test error rate, and in particular, the former, so the training error rate, can dramatically underestimate the latter. In the absence of a very large designated test set that can be used to directly estimate the test error rate, a number of techniques, and this is what this whole chapter is all about, can be used to estimate this quantity using the available training data. Usually, you will only have the training data. This is the whole point of these chapters. Some methods make a mathematical adjustment to the training error rate in order to estimate the test error rate. So chapter 6 is taking the training error rate and maybe passing it through a formula which would then, I guess, under certain assumptions, give you the test or an estimate of the test error rate. But that's chapter 6. In this chapter, we instead consider a class of methods that estimate the test error rate by holding out a subset of the training observations. So like what we did in the market data, the up-down, where we didn't use the 2005 data for training. So holding out a subset of the training observations from the fitting process and then applying statistical learning method to those held out observations. In sections 5.1.1 until 0.4, for simplicity, we assume that we are interested in performing regression with a quantitative response. So this is back to chapter 3, linear regression, for instance. In section 5.1.5, we consider the case of a classification with a qualitative response. Now, as we would expect, the key concepts remain unchanged, regardless of whether the response is quantitative or qualitative. So let's get started. Suppose that we would like to estimate the test error associated with fitting a particular statistical learning method on a set of observations. Okay, let's see. The validation set approach, displayed in figure 5.1, is a very simple strategy for this task. It involves randomly dividing the available set of observations into two parts, a training set and a validation set, also known as a holdout set. The model is fit on the training data set, and the fitted model is used to predict the responses for the observations in the validation set. The resulting validation set error, typically assessed using mean square error in the case of a quantitative response, provides an estimate of the test error rate. We illustrate the validation set approach on the OTO dataset. Recall from chapter 3, and we can see this very quickly. I'll just have a new script over here. So as always, library ISLR, ISLR, and we'll tell them data auto there. And one of the very first things that we typically do is type structure. So this is the data set with 392 observations. And for instance, you may wish to regress acceleration. Why don't we attach auto, and now we can, for instance, take acceleration. Why not take the weight, so the car's weight against acceleration, and that's over there. As you would expect, there's a negative. Should I call it correlation? There is a, yep, I'm going to call it correlation. There's a negative correlation. The heavier the car, then the less likely it is to have a high acceleration. And we can do ln. We could call it the weight acceleration fit lm. Give it the formula. Let's regress acceleration on weight. It's a simple linear regression, meaning a single predictor variable, auto dataset. Now what's interesting is that we have subset over here, and we kind of use this, although we didn't type it, we kind of used it yesterday when we had typed train. We might be using it in this chapter. And if you do summary of this, then you get your parameters. Note the p-value, triple asterisk, so highly significant. We reject, in this case, we reject the null hypothesis that there is no relationship between acceleration and weight. And you can now use this to make predictions. How then? Predict object. So I don't know, maybe when the acceleration is 50. You need to type a couple of other things, surely. It's not entirely clear. So this certainly would not work, right? I think we need to tell it using. Yeah, I would have been surprised if that worked as well. But if we just focus on the slope on beta 1, although beta 1 is what kind of looks like a very small number, you know, 0.001, when compared to the standard error, you can still safely say that with statistical credibility that it is not zero. You might want to change the maybe instead of the weight might be in kilograms, maybe choose to work in tons, just so you don't get a number that looks very small. So we illustrate the validation set approach on the auto data set. Recall from chapter 3 that there appears to be a non-linear relationship between miles per gallon and horsepower, and that a model that predicts miles per gallon using horsepower and horsepower squared gives better results than a model that uses only a linear term. It is natural to wonder whether a cubic or higher order fit might provide even better results. We answer this question in chapter 3 by looking at the p-values associated with a cubic term and higher order polynomial terms in a linear regression. But we could also answer this question using the validation method. We simply split the 392 observations into two sets, a training set containing 196 of the data points and a validation set containing the remaining 196 observations. The validation set error rates that result from fitting various regression models on the training sample and evaluating their performance on the validation sample using mean squared error as a measure of the validation set error, bit of a long sentence, are shown in the left-hand panel of figure 5.2. Let's have a look. So we're taking degree of polynomial. So degree one, and maybe degree 0 as well. Maybe degree 0. What are the different colors? I think each color is for a different. Each color is for a different. What are we referring to these? Either a holdout data set or also known as a validation set, right? Let's just get our vocabulary. So a validation set or a holdout set. So this is what you would exclude from the model fitting. And look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have sort of done the exercise 10 times. Each time we are excluding half of the full data. So let's take, for example, I don't know, let's take the yellow. So the yellow is before we start discussing the degree of the polynomial, degree 0, degree 1, degree 2, degree 3. Before we do that, we first choose from the 392 observations, we cut the data, and we say this half we're going to exclude. Once you've made that decision, you take the remaining data, the training data, you fit miles per gallon regressed on horsepower, once for horsepower to the 0, then with horsepower to the 1, horsepower squared, until horsepower to the power of 10. And for each of, I guess it's 11, for each of these 11, because we have from power 0 to power 10. For each of these 11 models on the same training data, you then calculate the mean square error on the validation, on the holdout data. And what we can see is repeating this procedure 10 times seems to give us the lowest errors are like around 4 power 7, roughly. I mean, obviously, then I guess you'd average over all the different holdout data sets. Let's see what the book has to say. The validation set mean square error, that's one, this is one number. Validation set mean square error, okay? The mean square error, do we want to just in case, we go to the start of this book and search mean square error. We do remember what mean square error is, right? Mean square error is this formula. So we're calculating it for the training. No, excuse me. We're calculating it on the holdout data, on the data that we didn't use to fit the model. So think of having on what we call the validation, think of a subscript over here. The mean square error of the validation data set. It's just the difference between the prediction and the actual observation. In actuarial work, very often we have sections in our reports which bear the title actual versus expected. It's abbreviated to AVE. And it's practically the same concept over here. So let's just go back to cross validation. That's over here. So what we're saying is the validation set mean square error for the quadratic fit is considerably smaller than for the linear fit. This is a lot less than this. Now, how did they calculate these? I would imagine, excuse me, the linear fit is this one. Okay, so this is considerably less than this. And I would imagine if we color code these things, is this pink just the average of these 10 over here? Let's see, it's 22. That kind of makes sense, right? It's between 19 and 29. Well, no, it's between, it only goes as up to here. Yes, I mean they're mainly over here, right? So that would be around 22. However, the validation set mean square error for the cubic fit is actually slightly larger than for the quadratic fit. So this cubic is actually slightly larger than the quadratic fit. This implies that including a cubic term in the regression does not lead to better prediction than simply using a quadratic term. Recall that in order to create the left-hand panel of figure 5.2, we randomly divided the data set into two parts, a training set and a validation set. If we repeat the process of randomly splitting the sample set into two parts, we will get a somewhat different estimate for the test mean square error. As an illustration, the right-hand panel, figure 5.2, which we were discussing earlier, displays 10 different validation set mean square error curves from the auto dataset, produced using 10 different random splits of the observations into training and validation sets. All 10 curves indicate that the model with a quadratic term has a dramatically smaller validation set mean square error than the model with only a linear term. Furthermore, all 10 curves indicate that there is not much benefit in including cubic or higher order polynomial terms in the model. But it is worth noting that each of the 10 curves results in a different test mean square error estimate for each of the 10 regression models considered. So there's some very long sentences over here for the simple reason that you kind of have, you calculate the mean square error for each validation set for each fitted degree from 0 to 11. This is why the sentences get so long, because you kind of have this compounding effect. For each training or for each validation data set, we need to fit each of the 11 degree regression models. But it is worth noting that each of the 10 curves results in a different test MSE estimate for each of the 10 regression models considered. I just read that. And there is no consensus among the curves as to which model results in the smallest validation set mean square error. What do we mean by no consensus? In the sense that sometimes your quadratic is the best. So for example, looking at this purple one, the one above yellow, quadratic does give you the best mean square error. But in this red one, the one just under the orange, you get a better mean square error for the higher than 2 degree polynomials. This is what we mean by there's no consensus. Based on the variability among these curves, all we can conclude with any confidence is that the linear fit is not adequate for this data. The validation set approach is conceptually simple and is easy to implement, but it has 2 potential drawbacks. As is shown in the right-hand panel figure 5.2, the validation estimate of the test error rate can be highly variable depending on precisely which observations are included in the training set and which observations are included in the validation set. In the validation approach, only a subset of the observations, those that are included in the training set, rather than in the validation set, are used to fit the model. So what's point number 2 telling us? That the price we pay in order to perform cross-validation, I shouldn't have said cross-validation, I should have just said validation. I think cross-validation is only one type. But the price that we pay in validation is that to fit the model, you're not using all of the data. Since statistical methods tend to perform worse when trained on fewer observations, this suggests that the validation set error rate may tend to overestimate the test error rate for the model fit on the entire dataset. Let's see what we're saying over here. The validation set error rate may tend to overestimate the test error rate for the model fit on the entire dataset. I think we can move on. In the coming subsections, we will present cross-validation, which is a refinement of the validation set approach that addresses these two issues. And maybe there are different types of cross-validation. The first one would appear to be leave one out cross-validation. And I think it's very easy to guess what we're going to do over here. It's abbreviated to LOOCV, is closely related to the validation set approach of section 5.1.1, what we've just done, but it attempts to address that method's drawbacks. Like the validation set approach, LOOCV involves splitting the set of observations into two parts. However, instead of creating two subsets of comparable size, a single observation is used for the validation set, and the remaining observations make up the training set. The statistical learning method is fit on the n-1 training observations, and the prediction y-1 is made for the excluded observation using its value x1. Since x1, y1 was not used in the fitting process, mean square error 1 is going to equal what? Well, it's going to equal y1 minus the fitted model's prediction. So maybe they'll write it as f subscript 1 hat of x1, everything squared. They chose not to. They chose instead to use the hat notation. The one drawback is that, well, I guess it's pretty obvious. I was going to say that you're not emphasizing that you've used the first fit. You haven't used the first model to estimate y1 hat, but the way this is structured, it will always be the first model that estimates y-1, then the second model that estimates y-2, and we're seeing it over here. So blue is the training, pink is the holdout, the validation data. And the full available data set is the white. Okay, so we are going to perform n fits. So for example, for the auto data set, you are going to fit it you are going to perform 392 fits. So this expression provides an approximately unbiased estimate for the test error. But even though mean squared error 1 is unbiased for the test error, it is a poor estimate because it is highly variable, since it is based upon a single observation. So what do we then do? We repeat it for x2 and repeat it for x3, etc. And then what we calculate is we calculate the mean of these mean square errors. What does CV stand for? Is it just cross-validation? Yeah. So the leave one out cross-validation estimate for the test mean square error is the average of these n test error estimates. Would you like to do this in R? I think so far the idea has been pretty simple. And how would we do this? How would we do this? So it was MPG on, let me just go back to the book. I'm not sharing it. Oh yeah, horsepower. You might want to see. Right, so that's why we took a quadratic. It's just not quite linear, is it? It might have like quadratic features. And we can include a quadratic term like this. We could even why are there only two coefficients? Or did I not run this? That's interesting. If I was expecting the intercept estimate, the horsepower estimate. Wouldn't we also expect an estimate for horsepower squared? Or does it not work like that? Let's do horsepower. Two. Okay. Horsepower. Yeah, isn't it like this? Do we have the code in R? Look, we're expecting these three coefficients. So I've clearly done something wrong in R. Let's see. No luck over there. So I wonder, what are you meant to do it? If necessary, we'll just scrap. So that gives you those two values. What if I type horsepower squared? Does it give you the same values Yeah, that's odd, isn't it? It gives you the same 39 and negative 0.15 as we got over here. So I'm clearly doing something wrong. But let's work like this. Let's just keep it as a linear relationship. Now how would you do it for the 392 times using the leave one out cross-validation approach? Well, first of all, this is a for loop. We'll take a dummy variable. We'll take I, for instance, and as a vector, we could say, is there the length of auto 9? So that's not what I want. So that's counted the number of fields in the auto data set. So what if I do dimension? Or is it just DIN? But we need just the first one, 392. So you could say like this, and just to make sure everything has worked, can we just do something simple? Just say something like or I could simply run this part, right? Yeah. So it's going to take from 1 to 392. Now what we need is we need this, but we're going to take out one value each time, one observation, beg your pardon. So how would that work? Well, let's just see it. Let's just run it over here first. What if I do auto and I take out the first row? Would it work like this? Probably. Yeah. In fact, it starts from 2. If you do auto -1, you've removed the second row. If you do like this, you'll now see that we're going to have 1, but then it jumps to 3, meaning I can now do this -I, and that should work. So it's going to do it. It's going to do it 392 times. But then I want maybe just one of the coefficients. Just one of the or no, both coefficients, because we're going to predict, right? We're going to make a prediction. We have to compare the MPG. So let's have a look. So what I'm saying is, if we do head auto, the first time that this loop is run, we then need to predict the MPG on the basis of the horsepower. Meaning what? Meaning, let's think of the first run. The first run, it will do LM on the full data set with the exception of the first row. But then what do we need? We need the MPG. We need the MPG actual. The MPG, these are just terms I'm defining. We need to save something into each one. Expected. And then we have the MSE would equal the MPG. well, we're squaring, right? So it doesn't really make a difference what I start with, but I think the book had MPG actual minus MPG expected. So let me just make sure that you agree with me. All I'm doing at this point is I'm going to calculate this, but the loop is going to do it for each one. So yes, it will calculate for the first observation, but then for the second, for the third, etc., etc. So we're going to have to save these MSEs. We definitely need that MSE saved. So what we could say is initially MSE is the null vector, and or let's say MSE collection. And into MSE collection, we take the previous MSE collection. So for example, if this is on the 5th run, it takes the MSE collection that has the first 4 mean square errors, like this, and it attaches the newly calculated MSE. Now, what we need to do is actually see how we're going to create these two. MPG actual, that's not a calculation. We know it. We know it. So what I would have to say is auto the ith row, and this is probably a better way of doing it, but I'm just going to count. Well, in just the first one. So for example, if this is 5, this should give me 17. 5th row, first column, and that gives 17. So that appears to work. Now the expected depends on the fit. So this is going to be y equals mx plus c. So we need, let's say we do this, removing the first one. Now, is there a way to get coefficients? If I do coefficients, and has that worked? That has indeed worked. And then you need to extract the intercept term, which is probably just 1. And also the slope parameter. So what will I say? I will say beta naught is my linear model I think I need to take a summary, or can I just say coefficients? I think I can just say coefficients. You can just paste it like this. Same thing for my beta 1. And now do y equals mx plus c. So I will say beta naught plus beta 1 times, and we're regressing on horsepower. And you just give it horsepower. So it is auto I row, and 1, 2, 3, 4 for horsepower. Now, this would be highly unusual if it works the first time round. We just get an idea. And maybe it worked. Maybe it worked. What we'll do is, I want to get rid of these horrible names. Did we have that in another sheet where we removed unname? So on, is it double N? No, yeah, it is. Unname. Same thing over here. Unname. Very fast, isn't it? I mean, it's performed. Was it 392 linear regressions? Yeah. Okay, so it's still looking a bit horrible, but you could round it to for example, 2 decimal places. So this is the mean square error. Now, is this even correct? Might be a good idea to maybe check this one, for example, the 2.02. So anyway, never mind that. We're just going to assume it's correct, but never a good idea, right? To just assume that your outputs are in fact correct. But the idea is, just to go over this again, I started with an empty vector. It's to save within it, I shall save every calculation of the mean square error. So think of it as your, well, it is in fact, the mean square error I. Each value, so for example, this one is the MSE subscript 100, because this one's the 99th. You take your data, but you remove a row. Each time, for each run within this loop, you omit a row of data. You're moving these, I don't know, what are they, salmon colored. The book's referring to them as beige. It's not beige, is it? Anyway. Right. So you remove one, for example, you remove the first row, you remove the first observation, you perform the fit, you save it over here, and from this fit, you extract beta naught, that's coefficients 1, and beta 1, that's coefficients 2. You get the actual MPG for the excluded observation. You calculate the expected MPG, and that's what? It's beta naught, beta 1 times the VAT. Now what does that 4 represent? That 4 is just the horsepower. Then you calculate the MSE and save it within your vector. And you do this 392 times. That is as many observations as we in fact have. Now I've saved it over here, and let's call this MSE collection rounded. And now we can calculate the leave one out cross-validation mean squared error by just calculating the mean. The mean of, I'll just take the rounded one. And like that, and like this. And there you go. So 24.23. Now, what would be interesting is but we can't seem to get it to work, is what if you had horsepower and horsepower squared? Would we get, using the leave one out, would we get a lower mean squared error or a higher mean squared error? And that gives you an indication of what degree polynomial one should have in terms of the horsepower predictor variable. Now, is it worth wasting a few seconds to go to the labs of chapter 3 and see if perhaps I'm not going to zoom in just because I want to get this to see how you meant to include higher powers. So wherever we have LM, poly, this looks promising. Poly L-stat 5. What is this? Let's see. L-stat squared term. L-stat squared. So the way we were meant to do it, had we, so I think what we've done is we've well, not accidentally, but we've ended up skipping part of the lab of chapter 3. And we definitely skipped part of the lab of chapter 4 as well, because I just wanted to move on to this new chapter, but interaction terms. This is it. The LM function can also accommodate nonlinear transformations of the predictors. For instance, given a predictor x, we can create a predictor x squared by using, you need to use I. That's why it wasn't working. The function I is needed since the hat has a special meaning in the formula. Wrapping, as we do, allows the standard usage in R, which is to raise x to the power 2. We now perform a regression of med v, whatever that was, onto L-stat. This is how you need to do it. So hopefully we can consider this as us having learned something else. A better approach involves using the poly function to create a polynomial within LM. For instance, the following command, produces a fifth order polynomial fit. Now, that gives me an idea. I'm not necessarily saying we're doing it, but you could have a loop within a loop. You could have poly this, comma j, for instance. Let me call it n. Maybe not n, I'll call it k. And this 4, I'm not going to do it this way because it will probably take too much time. But you could in fact have a loop within a loop. So it would you would create this way. You would create the mean squared error for the leave one out for polynomial order 1, polynomial order 2, 3, 4, 5. We can do it manually, but please do keep in mind there is absolutely no reason to do it manually. But let's just see if it works. And I'm looking at the book just to make sure. Horse power squared. Before I do anything, let's see if this actually works. Very good. Now it gives us what you would expect. 3 parameters since it's a quadratic. And if I tell it this, it does in fact give the third coefficient, which would be the quadratic coefficient. So let's just run this again. Okay, that's what we had earlier. Ah, why is it 397 now? Let's remove this for a second. We had 24, right? Earlier. Uh-oh. Do I need to remove this bracket? Okay, so that's the 24 we had from the linear model. What do I mean by linear model? I mean, adding horsepower squared, it's still a linear model, but it's linear now on not just horsepower, but horsepower and horsepower squared. So what I would do, and I'm doing this very manually, I horsepower squared. Now I need to introduce a third coefficient. And in the formula, I would need to define beta 2 times the horsepower value squared. Okay. And that should hopefully work. If you see anything that looks off in my code, do let me know, please. It's the same principle, but we're going to regress on horsepower together with horsepower squared. So you actually have three coefficients: constant, linear, and quadratic. Constant, linear, and quadratic. We'll see if we get a lower or higher mean square error. Gives you an idea of whether you should include these higher degree relationships. Like this. And now it's 19.24. So you get 24 over here and 19 over here. I wonder if they actually do it in the book. If we go to horsepower, they mention horsepower in the lab section. They actually seem to be doing it over here. Now they're using a specific command, the cv.glm, but isn't that 24 the 24 that we had? 24.23. So we actually seem to have the same number as they do. And isn't this incredible? They have done it for 5 different models, and their 19.25 is our 19.25. So it's always nice when these things are these sessions are extremely improvised, and this is one of those times where maybe the improvisation is going in our favor. The only loop that they have is calculating. It is reflecting the different degrees: degree 1, degree 2, until degree 5. When we say degree, I'm sure you all remember, degree just means the highest power. Excellent. So I think we're doing something right, aren't we? And we use this formula. We used it twice, once on regressing on horsepower and to calculate that 24 point something, and a second time regressing on horsepower and horsepower squared to get that, was it 19.25. As we progress through this chapter, we're going to see quicker ways that avoid using all this code. But the code itself would be based on some kind of the logic reflecting what we have in our own code. LOOCV, so this is the leave one out cross-validation approach, has a couple of major advantages over the validation set approach. First, it has less bias. In the leave one out, we repeatedly fit the statistical learning method using training sets that contain nearly all of the observations. N-1, in fact, that is almost as many as there are in the entire dataset. This is in contrast to the validation set approach, in which the training set is typically around half the size of the original dataset. Consequently, the leave one out approach tends not to overestimate the test error rate as much as the validation set approach does. So the yeah. Second, in contrast to the validation approach, which will yield different results when applied repeatedly due to randomness in the training/validation set splits, performing the leave one out multiple times will always yield the same results. There is no randomness. What do they mean by there's no randomness? You're not randomly saying, okay, let me select this 50% of the data, or let me select this 50% of the data. In leave one out, you always use the same steps. So your first mean square error, that's based on all of them excluding the first, etc. We use leave one out on the auto dataset in order to obtain an estimate of the test MSE that results from fitting a linear regression model to predict miles per gallon using polynomial functions of horsepower. The results are shown in the left-hand panel, figure 5.4. And this is what, let's see. One is over here, isn't it? If you look at the scale, 2 to 4, this is 3. So look. This is R24. We got this in using R, and it goes down significantly to 19. So we have significantly reduced. It's like by 20%, isn't it? Leave one out has the potential to be expensive to implement since the model has to be fit n times. This can be very time consuming if n is large. I mean, imagine we had 10 million observations. And if each individual model is slow to fit. With least squares linear or polynomial regression, an amazing shortcut makes the cost of the leave one out method the same as that of a single model fit. Okay, so let's just back up for a second. So there's this formula, and immediately we need to start reading a bit. We need to read it carefully. So the way this has changed is this denominator, right? The 1 minus hi. That, I mean, we're nearly there. We're nearly there. Might be additional detail that we don't need to know. Something called a leverage on page 98. Now isn't that something that we would have come across if it's on page 98? Oh. Yeah. This whole thing over here. Okay, we may have skipped a few pages towards the very end, which probably we can do without. But we are now mentioning this concept over here. in order to quantify an observation's leverage. So is leverage observations with high leverage have an unusual value for xi. For example, observation 41, figure 3.12, no, 3.13. Observation 41, I see. So leverage, think of the physical process of leveraging something. So you have some kind of mechanical interaction, like what are those things at play parks? A seesaw, right? And 41. I mean, changing these data points over here, they're not really going to impact the red. Is the red the fitted? The red line is the fit. Oh look, blue. It does change quite a bit, especially if you're making predictions for observations that have an x value between 3 and 4. It changes the blue to with the 41 you have the red, without the 41 you have the blue. Okay, and in fact there's a formula that kind of quantifies the leverage. You can calculate the leverage for every observation, and 41 has the highest leverage. It also has something called the studentized. There is a probability distribution. There is a random variable called the student T random variable. Residuals. We can probably live without this for the time being. But apparently you can do just one fit. So, you know, chapter 3's least squares fit. I would imagine using all the data and using HI, which is the leverage. So you calculate the leverage for each observation. If you perform this calculation, that's the same as averaging out each individual mean square error. Okay, we'll take their word for it. The leave one out approach is a very general method and can be used with any kind of predictive modeling. For example, we could use it with logistic regression or linear discriminant analysis or any of the methods discussed in later chapters. Now, the magic formula 5.2 does not hold in general, in which case the model needs to be refit n times. Yeah, so this only works for regression, and specifically it needs to be least squares, linear or polynomial regression. You're certainly not going to use it in, for instance, a classification model where the y isn't even a numerical value, let alone how much you're going to subtract those y's. Okay. Now, this is probably a more general approach. An alternative leave one out cross-validation method is k-fold cross-validation. This approach involves randomly dividing the set of observations into k groups or folds of approximately equal size. Of approximately equal size. Okay, so for example, over here we've partitioned, beg your pardon, we've partitioned the data into five into 5 sub data sets. Why did they write 1, 2, 3? I think they wanted to write 11, 76. For example, over here, 1, 2, 3. And they wrote 1, 2, 3. Well, actually, 1, 2. Right, because what could be happening is that maybe the first, second, and third all went into this one. They're kind of doing a bit of, yeah. Okay. Still, I would have maybe kept the order, because all you're doing is you're just drawing a line, aren't you? Okay. Randomly dividing. Maybe to reflect that we're kind of randomly dividing. We're not just saying the first so many observations, the next so many observations. So into K groups or folds of approximately equal size. The first fold is treated as a validation set. And the method is fit on the remaining K-1 folds. The mean squared error, MSE1, is then computed on the observations in the held out fold, as you would expect, right? So it really is like, yeah, the leave, if I just skip to this for a second, the leave one out is a special case of K fold, in which K is set equal to the number of observations. In practice, one typically performs K fold CV using K equals 5 or K equals 10. What's the advantage of using K equals 5 or K equals 10? The most obvious advantage is computational, right? So instead of, for instance, in the auto dataset, you would have to perform 392 fits and calculate the validation mean squared error for each one. If you're dividing your data into just, if you're doing, over here, you're just doing it 5 times. Yeah, so this is, it's really the same, isn't it? It is identical to leave one out. Obviously, now we need to look at this trade-off, the bias variance trade-off. Depending on your K, if it's 5, if it's 10, and then we'll do cross-validation. I think we're doing well for time, aren't we? If you want to break, I probably should have asked earlier. We want to break, we can take 5 minutes. Just let me know in the chat. Otherwise, I'll leave it up to you. So this is now the classification problems. We will then move to Bootstrap. Okay, let's do 5 minutes. Just message me directly. I'll know when to continue. Let's aim to do around 5 minutes, please. And I'll pause the recording for the time being. Let's continue reading. Most of it is repetition. We'll just say cross-validation is a very general approach that can be applied to almost any statistical learning. Some statistical learning methods have computationally intensive fitting procedures, and so performing leave one out may pose computational problems, especially if n is extremely large. On the other hand, performing 10-fold CV requires fitting the learning procedure only 10 times, which may be much more feasible. As we see in section 5.1.4, there can also be other non-computational advantages to performing 5-fold or 10-fold CV, which involve the bias variance trade-off. Right. So are we comparing? Let's have a look. We have the leave one out estimate is a black line. are these three different models. So I think it's for three different data sets. We have tenfold is orange. And they basically mirror each other, don't they? And the true test MSE, remember, using test data that you normally wouldn't have available. The authors, again, this is extremely important point. The authors have the true test available because they're using simulated data. Whatever they did over here, we're not saying the actual data set, but they used simulated data. They knew the parameters in advance of the distributions. They knew the betas in advance. They knew the epsilon in advance. And well, what we see is there is a tendency to underestimate the true mean squared error. And what is this horizontal axis? So it's clear this is the mean squared error. I wonder if the flexibility is kind of like just kind of like what we had earlier in terms of like the degree of the polynomial. Degree 2, degree 5, degree 10, degree 20. So what you'll see is that in actual fact, it's a degree 6 that minimizes the true mean squared error. Instead, using leave one out or k-fold, we'll conclude that we should use this degree. Yeah. Okay, so hopefully this makes sense to us. Using the leave one out is computationally prohibitive, is the word the book uses. Happily, tenfold CV, at least in these three cases, seems to mirror it reasonably well. And obviously it comes at, it's a lot faster to implement, and it doesn't take that much computational processing speed. The right-hand panel of figure 5.4 displays figure 5.4. This. Oh, okay. So this was leave one out. These are actually tenfold. So we're going to have 10 curves because we're going to split the data. So tenfold will be you exclude 10% of the data. So you fit on 90%, predict on 10%. Then again, fit on 90%, predict on 10%. Each time you'll get a different curve. And remember, we're using these to, at least in this context, to test which degree polynomial should we use. Should we just regress on horsepower together with horsepower squared, etc., etc. Okay. When we examine real data, we do not know the true test MSE clearly. And so it is difficult to determine the accuracy of the cross-validation estimate. However, if we examine simulated data, this is what we discussed earlier, just a few minutes ago. Then we can compute the true test MSE and can thereby evaluate the accuracy of our cross-validation results. In figure 5.6, and we discussed all this, in all three plots, the two cross-validation estimates are very similar, the orange and the black dotted line. In the right-hand panel, in figure 5.6, the true MSE and the cross-validation curves are almost identical. In the center panel, the two sets of curves are similar at the lower degree of flexibility, while the CV curves overestimate the test set MSE for higher degrees. In the left-hand panel, the CV curves have the correct general shape, but they underestimate the true MSE. They are lower than the blue. They get the shape right, U-shape, U-shape, but they get the minimum, they don't quite get the exact minimum. When we perform cross-validation, our goal might be to determine how well a given statistical learning procedure can be expected to perform on the independent data. In this case, the actual estimate of the test MSE is of interest. But at other times, we are interested only in the location of the minimum point in the estimated test MSE, and this to choose the degree of polynomial. This is because we might be performing cross-validation on a number of statistical learning methods or on a single method using different levels of flexibility in order to identify the method that results in the lowest test error. Remember, flexibility, just think of it as if it's a line that's zero flexibility to a great extent. If you start including higher powers, higher exponents, then you're increasing that flexibility. Now, of course, as always, there's this trade-off. Should you each additional degree, so let's say you've got up to a quintic, degree 5, should the question is what do I gain and what do I lose by including a further term with maybe exponent 6? We find in figure 5.6 that despite the fact that they sometimes underestimate the true MSE, all of the CV curves come close to identifying the correct level of flexibility. Correct level of flexibility is what we were looking at earlier, just the X value. So we don't really care that the Y values are off. We don't really care about this difference in Y value. What we care about is if the true flexibility, think of it as degree 6. Well, we're saying, I don't know, k-fold and leave one out are roughly telling you degree 8, perhaps. So you aren't getting it quite right, at least in this diagram, but it's much better than just blindly saying, okay, let me take quadratic. Whereas in fact, you should increase the flexibility and work somewhere in this neighborhood where you are significantly reducing the mean squared error. Pretty cool stuff, right? Bias variance trade-off for k-fold cross validation. We mentioned in section 5.1.3 that k-fold CV with k less than n, naturally, has a computational advantage to leave one out. But putting computational issues aside, computation meaning the processing speed, the time, aside, a less obvious but potentially more important advantage of k-fold CV is that it often gives more accurate estimates of the test error rate than does leave one out. And this has to do with the bias variance trade-off. It was mentioned in that section that the validation set approach can lead to overestimates of the test error rate. So it gives you incorrectly a much higher test error rate than your model deserves to be assigned. Since in this approach, the training set used to fit the statistical learning method contains only half the observations, right? So the less data you use, the more variability there's going to be, the more uncertainty there's going to be. Using this logic, it is not hard to see that leave one out will give basically unbiased estimates of the test error, since we're using practically the entire training data set with the exception of one observation. And performing k-fold CV for, say, k equals 5 or k equals 10 will lead to an intermediate level of bias, since each training set contains how many observations? Each training. So you have your n, and you're left with what fraction of your observations? Do you remember when I was saying 90%, 10% in 10-fold cross-validation? Each time, aren't you using 90% to fit and 10% to calculate the MSE? Well, you can always create that fraction, 10%, 90%, by using the ratio k minus 1 out of k. You are splitting the data into k portions, and from those k portions, you're using k minus 1 of those k portions. That's from where we get this fraction. So it's fewer than the LOOCV. So to leave one out, uses practically all the observations, n minus 1, but substantially more than in the validation set approach. Therefore, from the perspective of bias reduction, it is clear that leave one out is to be preferred to k-fold, because leave one out uses nearly all the data, so there's less uncertainty in the data that we're using. So that's from the bias. That's from the standpoint, from the perspective of bias. However, we know that bias is not the only source for concern in an estimating procedure. We must also consider the procedure's variance. It turns out that leave one out has higher variance than does k-fold cross-validation, with k is less than n. Why is this the case? When we perform leave one out cross-validation, we are in effect averaging the outputs of n fitted models, each of which is trained on an almost identical set of observations. Therefore, these outputs are highly correlated with each other. So there's a very high amount of bias over here. In the leave one out, each time you calculate the mean squared error by omitting just a single observation, you're basically using the same data set each time. In contrast, when we perform k-fold CV, where k is less than n, we are averaging the outputs of k fitted models that are somewhat less correlated with each other, since the overlap between the training sets in each model is smaller. Since the mean of many highly correlated quantities has higher variance than does the mean of many quantities that are not as highly correlated, the test error estimate resulting from leave one out tends to have higher variance than does the test error estimate resulting from k-fold CV. How important is this? I think we just need to, it's the result that's important. One performs k-fold cross-validation using k equals 5 or k equals 10, as these values have been shown empirically. So empirically just means using actual data sets to yield test error rate estimates that suffer, and this is the Goldilocks zone, right? Neither from excessively high bias nor from very high variance. This is all we need to keep in mind. When creating a model, you need to minimize the bias while minimizing or getting as low of a bias as as low of a variance that allows, and apparently we get this with a 5-fold or a 10-fold cross-validation approach. Now, same kind of principles, and I'm just going to look something up online. I don't have my clock on me, so I'm just going to type time. Okay, so I know that we have around 20 minutes left. In this chapter so far, we have illustrated the use of cross-validation in the regression setting. So that means the outcome is quantitative, and so have used mean square error to quantify test error. But cross-validation can also be a very useful approach in the classification setting when Y is qualitative. In this setting, cross-validation works just as described earlier in this chapter, except that rather than using mean square error to quantify test error, we instead use the number of misclassified observations. So if it is misclassified, you get a 1. If it's classified correctly, you get a 0. And again, you want that your model reduces the number of 1s, because 1 means a misclassification. Think of yesterday when we were doing default does not default, and you want your model to hopefully classify all the defaults as defaults and all of the non-defaults as non-defaults. As you start deviating from that ideal scenario, then your error rate, what we're referring to as, the error rate starts increasing. For instance, in the classification setting, the leave one out error rate takes the form, so it's exactly the same thing, but now we just have error I, and this is the indicator variable. If they are not equal, you get a 1. So to think of that as a penalty. If they are equal, they are a 0. It gives you a 0 for each observation I. The k-fold CV error rate and validation set error rates are defined analogously, clearly. As an example, we fit various logistic regression models on the 2-dimensional classification displayed in figure 2.1 or 2.13. So that's this over here. Remember, it's 3-dimensional. Always look at it as 3-dimensional in this setting. X1 and X2, those are your 2 predictor variables. The colors, so these look like oranges and blues, are your 3rd dimension. Default does not default. Goes to court, does not go to court. Rains, does not rain. And we were here, right? In the top left panel of figure 5.7, top left, is that this one? This is top. So now we're looking at decision boundaries, aren't we? So is the black, given that it's degree 1, least flexibility, by the way, whereas degree 4, you're getting, well, more flexibility. Let's see. In the top left panel of figure 5.7, the black solid line shows the estimated decision boundary, and someone's knocking, just 1 second. So we're looking at figure 5.7, and exactly, the black solid line is the estimated decision boundary. Let's have a look at it. Degree 1, that's why it's a line, whereas when we move on to the other 3 diagrams, we're going to look at a quadratic decision boundary, a cubic, and a quartic. And what does the decision boundary do? The idea is In this panel, anything above the line is classified as orange. Anything below is probably going to be classified as a blue. And you can now calculate the error rate, right? You can say, I think there were 100 observations. Does it say that there were 100? No, but I seem to remember there were 100 of these. And you can easily, you can even just, with such a low amount of observations, you can actually just count them manually. 1, 2, 3, 4, 5, 6, 7. Well, maybe that was a bit optimistic, but you have around I don't know, 10 on this side, 10 on this side. So it looks like maybe a 20%. Oh, perfect. The test error rates for the 4 logistic regression are in fact, look, 0.201. And it's decreasing, it decreases, but then there's a slight uptick over here. So maybe now the model is too flexible and it's not reflecting the true subdivision within the data. So going back to what we were reading, the black solid line shows the estimated decision boundary resulting from fitting a standard logistic regression model to this data. Since this is simulated data, we can compute the true test error rate, which takes a value of 0.201, and so substantially larger than the Bayes error rate. What does that mean? The Bayes error rate of 0.133 might be something for tomorrow's session. Clearly, logistic regression does not have enough flexibility to model the decision boundary in this setting. We can easily extend logistic regression to obtain a nonlinear decision boundary by using polynomial functions of the predictors, as we did in the regression setting in that previous section. For example, we could use a quadratic logistic regression model. So now we have these additional 2 terms, x1 squared and x2 squared. The top right panel, figure 5.7, displays the resulting decision boundary, which is now curved. However, the test error rate has improved only slightly to 0.197. A much larger improvement is apparent in the bottom left panel. This one, look at this one. This is really great because you see this bulge over here. This is where we were really getting it wrong. These 2 bulges over here. But with the cubic, we're allowed to go around them. This is really great. Now the test error rate has decreased to 0.16. Going to a quartic polynomial slightly increases the test error. I think I'm going to finish over here. And what's really great is that we've made a lot of progress, haven't we? And to the point that we can now very soon start. We'll be doing this tomorrow. We'll have to discuss this idea, this formula. So that might be a job for Microsoft Word, where we'll do Bootstrap. But very quickly, that takes us to chapter 6, which is linear model selection and regularization. We'll just stop here.